The moon tilt illusion, also known as the Moon Terminator illusion. Today we're going to make a special emphasis on doing the math. So, warning, if you're allergic to math, you may want to skip this one or just skim through if you're interested in the tilt illusion and what causes it. The moon in this picture is lit, and this is the lighted side of the moon. And then we're going to pan over and see where the sun is and see that the sun is way down low on the horizon. Boom, there, look at that. The sun has set. The sun is below these buildings at least. Let's back up. Moon is up. Moon is lit from up high, but the sun is down low. And the reason I think this is probably a joke is the original author of this video calls out specifically this contrail that's right here. He calls it a chemtrail, but I want you to watch what happens to this very straight, almost horizontal line when he pans the camera. Just watch. I'm gonna pan the camera as we look over to the side. Whoa, wait, what happened to our horizontal line? It points almost straight down towards the sun, as if he did this on purpose. So I think this was a joke. I think he was trying to show you how the Terminator illusion actually works. If you saw my previous video on this, then you've already seen this demonstration. What I have here is a little simulation where I have a viewer looking up at the moon. Viewers looking up at the moon, you see that there. And then over here we have the sun, and I've placed it so that the moon is higher than the sun. And if we look over at the sun, we can see that the sun is down below the moon. But when we look at the moon looks like it's lit from above. And this line that connects the sun and the moon shows that, and it shows how that line rotates when you rotate the view. There was a criticism of this video that I did, or this simulation that I made, that it was not to scale. It was showing things too close. The sun is way too close. So I've redone it. And this is all done to scale. So I have basically the same deal. I have a sun, and I have a moon, and the Earth is in the middle here. Let's put it on the camera. Okay. So, and what I've done is I've arranged the moon and the sun on little rotator objects so that I can type in the polar coordinates that I want precisely, and that'll put the moon in those polar coordinates. So what coordinates did I choose? For the moon, we'll put the moon at 20.89 and 136.35. And the sun at 8 o'clock will be at 4 and 294.62. All right. Let's see the moon. See my little connector is still connected. Okay. I'm going to need to reorient the camera to look at that. Make it big. Oops, too high. It was at 20 something. And here comes the moon. There's the moon. So if we center that more or less in the frame, all right. So we see again, the moon is going to be lit from the right side and above. But if we want to find the sun, we're going to have to go down to the horizon. Sun will be setting at this point. In the west somewhere. There's the sun. Okay, so the sun is going to be down low, but the moon will look like it's lit from above. So with that, let's do the math. Here's a paper. right here. It's available online, where Andrea K. Myers-Beaton, sorry if I'm mispronouncing your name there, and Alan L. Myers of University of Pennsylvania have done an analytical derivation of the mathematical formula to describe this. What I'm going to look at is the angle, the apparent angle to the viewer that the moon appears to be lit from. And they have the equation all derived for us for that, and we'll go through that derivation. If the viewer is looking directly at the moon, what is this angle between the horizontal and this white line, which we'll call alpha? If I skip ahead in the paper to page 10, they have the final result for that right here. We'll go through this whole thing, but this is the money shot right here. Alpha is the angle between the horizontal and the apparent light, where a positive alpha means that the light appears to be coming from above the moon. And these are all terms, well, this is some trigonometry, and then these are all terms regarding where the moon and the sun are, where the m's are the moon and the s's are the sun. And the delta is defined for us right here, which is just the moon's angle minus the sun's angle. So before we go into that, let's take a look at exactly what these terms are and make sure we're getting them right. So here's this diagram where they define these angles. The angle phi is going to be the azimuth angle to the specified body. So phi sub m is the azimuth of the moon, phi sub s azimuth of the sun. As they're describing right here, this diagram doesn't show the eta. That's the Greek letter eta, I think. Forgive me if I'm wrong on pronouncing that. I call that eta. That is not in this diagram. What they show instead is theta, which is the declination. Astronomers like to use declination, which is the angle down from straight up. Engineers like to use the ascension, or the angle up. So the angle from the horizontal up, which is just 90 minus theta, right? And so they're talking about that right here. We're going to use eta, which is this angle right there. So that'll be how high up above horizontal the object is. Okay, this is really useful. We're going to start off with a quick primer of spherical polar coordinates. R is the radius, which is the distance from the observer to the observed body. The theta here is that declination, and you'll see later on when we use these, we're going to need to convert that into the eta term, which is the one up, and then the phi angle, which is the azimuth angle. So these are the Cartesian coordinates, the x, y, and z coordinates of this point, given the r, theta, and phi. So let's skip ahead to page 5 here, where we're going to pick up with the actual equations here, the math. We're going to start with S and M. S is the vector from the observer to the sun. M is the vector from the observer to the moon. So this V is going to be the vector from the moon to the sun. Okay, and then use some math terms here, parametric equation for the locus of V. All we're saying here is that C is any point along, any point along the line from the moon to the sun, where lambda, we're going to let lambda go from 0 to 1. If we put in 0 for lambda, we get 1 minus 0 times m, so that's just m, plus 0 times s. So C, when lambda is 0, C is m. When lambda is 1, we're going to get 1s plus 1 minus 1 is 0, so 0m. So when lambda is 1, then we just get the answer s. So as we let lambda go from 0 to 1, C goes from m to s. Okay, this is because the authors are taking an analytical arbitrary solution to this at this point. We're interested in when the C, which is what the camera is going to be looking at, when C is looking at the moon. So we're just going to plug lambda equals 0 in right away from the start, and that will reduce some of the complexity of this math just a little bit. So let's move on to this diagram, figure 7 on page 8, where they're trying to explain everything visually with a diagram. Now, before we even go any further, it says clearly that this is not to scale. We shouldn't worry about that. This is a visualization of the math that we're going to do, and all the math will be using actual numbers. Nothing about the scale of this diagram is going to have anything to do with that. So the important terms here are the m, which is the vector from the observer to the moon, the s, which is from the observer to the sun, and then here's that v from the moon to the sun. Here is c, which is the direction from the observer to what the observer is looking at. They have done it as an arbitrary point on this line. We said before we're going to simplify and we're going to look straight at m. So c and m are going to be identical. So the next thing they want to do is they want to create this observer sun-moon plane, which is the plane that contains the observer, the sun, and the moon. The observer, the sun, and the moon together, they make a triangle, and they want to make that into a plane. I have here a simulation, a 3D simulation, to try and help us visualize this diagram. So I have here the moon, the sun, and an observer sitting on top of the Earth right here. So the observer is looking towards the moon, the observer looking towards the sun. This is M, this is S. And by putting in this 3D, we can look at it in different angles and really understand better what we're seeing. So we want to make a triangle out of this. So I'll complete the triangle by putting a rather important ray here from the sun to the moon. Sun to moon, let's turn that on. Okay, so that completes the triangle, and this is the direction that the light is coming from. And if we look at the moon here, we'll see that the light from the sun is shining there on that spot. Okay, so this completes our triangle. So the next thing they wanted to do in that diagram was turn this triangle into a plane, which I have right here. Here's a plane to help us visualize that diagram better. This is the plane that that triangle lives in. If we take these 3 points, observer, moon, and sun, 3 points defines a plane. Okay, that is this plane in their diagram. If we have a point and a perpendicular to the plane, that perfectly defines a plane mathematically. We'll take a point in this plane, and then we're going to need a perpendicular, a vector that is perpendicular to the plane, and we can get that with a cross product. Cross product, one of the interesting and perhaps most useful features of cross product is that a cross product gives you a new vector that is perpendicular to both of the input vectors. So if we cross S and M, we're going to get this vector that is perpendicular to the entire triangle made by OSM. So we'll do that, and that will be needed for this part right here. So that's the S cross M. The next thing they want to do with this diagram is they want to show a viewing plane. The viewing plane is just a plane, that's this square here, rectangle here, that is perpendicular to the direction that we're viewing. So we said once again that we were viewing straight towards the moon. So let's see how that looks in our little diagram. We'll be looking from the Earth up towards the moon. In fact, here's the camera. Shows our view looking up towards the moon. There's the camera's view frustum there, the pyramid shape of what the camera can see. So let's make a plane. We're going to slice right through this pyramid, perpendicular at some distance. Whatever distance looks good. Okay, so that's this plane. That plane slices through our view. The reason that's interesting is because we can imagine this plane as a window. Imagine you are sitting in your house looking through a square window. You're sitting perfectly still, close one eye, just see a perfect view of what's in front of you, and then draw with a marker what you see in front of you. If you're going to draw where this moon looks to you on the window, all you got to do is draw a straight line from the moon to your eye, and right in front of you, right where you see it hit the window, that's where the moon appears to be. So this is that window seen from the camera's eye. That point right there is this intersection right there. Let's show that. So there you go. I have calculated using the intersection math of this ray and this plane the exact location of where that is. And if we again show that from the camera's eye, we'll see that that intersection nails right on top of the moon. Tell you what we'll do. We'll put this over here so we can see them side by side. That intersection should be right on top of the moon. At this point, we've got the observer sun-moon plane, and now we've got the viewing plane. And what we're going to see is the intersection of those two planes going to create this line. And along that line is the apparent light direction of the sun to the moon. Actually, we are doing our math in the opposite direction, so we're going to get a line from the moon to the sun, but the apparent lighting direction points in that way, pointing back towards the sun. So if we think about it this way, this is the line from the moon to the sun. We're just going to project that onto the view plane. And wherever that line hits the view plane, that's the line that it's going to look like. So actually we did that right here. They're calling this P. P can be gotten as C cross S cross M. Now, why is that? Review, S cross M is the perpendicular of the observer sun-moon plane. And the perpendicular of the view plane is, of course, C. So if we cross those two perpendiculars, we get the mutual perpendicular. We get the line that is perpendicular to this plane and to this plane, which is the line that the two planes intersect. Okay, so that's this math. One other thing to remember is that we're going to do the special case where C equals M. In their diagram, they've got the view plane looking this way, so it's really easy to project the sun's point back onto the view plane and the moon's point back onto the viewpoint. The whole point of this exercise was to get anything, any portion of this line V projected, because this entire line V projects back as this entire line segment. We need any portion of it. We only care about the direction of P, so any point will work. We have, let's look at it again, we have changed things a little bit. We have the viewer pointed towards the moon, and the sun is back behind the view plane. So getting the point where the sun intersects the view plane is not going to work well for our visualization. So I'm going to use this line segment right here from the moon back to the intersection as my line that we're projecting onto the view plane. It's the exact same result. I'm just choosing two different points along that line. I'm choosing this point. I'm going to project it back to here. You'll see that's right here. And a point a little bit further on, and we'll project that one back. Boom. So we're going to get a line segment that looks like this, but the direction of my line segment and the line segment P are going to be parallel. So I'm going to connect these 2 points with a line segment right here. Bada bing. Okay, this line segment represents the intersection of the view plane and the triangle. So this piece is significant because this piece represents the apparent angle that the light is coming in to the moon. Let's take a look at that. I will turn it off and see, here's the light coming in from the sun to the moon. This is this line right here. And in this view plane, that's perfectly parallel to this red line that I've just drawn. Okay, so now we have this P vector, which we got from this formula right here. Just do a couple cross products. And now we're going to take it to this diagram. We're looking now edge on to this 3D diagram. Ultimately, our goal is to find this little angle here in this diagram called gamma, which this little angle is the angle between the observer's horizontal and the observer's projected lighting angle. So this is the observer's horizontal, we'll call that H, and we just calculated the observer's apparent lighting angle. So we're going to need H. Here's the little diagram showing how we get H. We're going to take the forward vector that the viewer is looking along, and then we're going to take the straight up vector, which is Z in their diagram. We're going to take the forward direction, and we're going to cross it with straight up. That's going to give us what is perpendicular to forward and up is to the right. So we're going to get a vector straight to the right as far as we are concerned. As far as the viewer, the observer is concerned, that angle is to their right. We're looking for this angle gamma, and the angle gamma can be gotten from this equation right here. The dot product of two vectors gives you a scalar that equals the magnitude of the first vector times the magnitude of the second vector times the cosine of the angle between them. That's the magic thing we're looking for there, is the angle between them. So if we just divide through the magnitudes, they go down here. This absolute value p represents the magnitude of vector p, and this absolute value h is the magnitude of vector h. So the cosine of gamma is the dot product of the two vectors divided by the product of their magnitudes. Another property that we can use here is that the cross product of two vectors has a magnitude equal to the magnitude of the first times the magnitude of the second times the sine of the angle between them. That's a useful little trick, because what the authors do next is they just take the cross product magnitude divided by the dot product, and then these magnitude values from the cross product and the dot product, those will cancel out, and we'll be left with just the sine of gamma divided by the cosine of gamma, which is also known as the tangent of gamma. So we have the tangent of gamma equals the magnitude of p cross h divided by p dot h. We're just going to now take this equation and substitute in what these values were. H equals c cross z, and so we'll put that right here as the h's go in, and this was the equation for the p. If you remember, p was c cross s cross m. And we'll get to this in a second, but we're just going to put m here when we do this. Okay, so this is just the substitution, and then if we go back quite a bit back, we had this for c. This was the definition of c from the paper. We had simplified it and just made it m. So we can cut through some of this, but they've gone ahead and put in the full form. That's just substituting what c is right here. That's all that is. All right, and then here they go ahead and do what I just said, which is to take the c and just make it m. So we're going to drop in the m right there and take out the c's. That'll simplify things quite a bit. And now they have changed the name from gamma to alpha. What they're doing there is they're just saying the special value of gamma that happens when m is put in instead of c, or when lambda goes to 0. We're going to call that special angle alpha. That's really the one we're interested in anyway, so we got there. Okay, the next thing you want to ask, why are there these little hats on top of the vectors? Something happened in here that they switched out the full vector for vectors with hats. They say that right here. The absolute values of m and s, for which we henceforth substitute the unit vectors m and s for computational convenience. What does that mean? When you put the hat on a vector, That means you're taking a vector in the direction of M, but with a length of 1. So this is a vector. This is a vector from the observer to the moon, but it's only a unit length. It's one unit long. It's not the entire vector. Okay, how can we get away with that? We can get away with that because you remember we took the magnitude of these. It was in the denominator, and those canceled out. So it doesn't matter what the magnitude of P is. The magnitude of P is going to be divided off of the numerator and the denominator. Back to the visualization, we're just looking for the angle between this line and the horizontal. We don't care how long the line is. We really don't. We only want the angle. So that's why we can simply say we're going to use the units. Okay, so we're down to this. The next step that they do is they take us out of vector land, and then they express this in terms of the 3 components that make up a vector: the x direction, the y direction, and the z direction. So, and then for convenience, they're going to express the dot product, which is going to come up here in a second. The dot product, they're writing as d, and here's the mathematical formula for a dot product. So, they're going to go off into an appendix to do some math and come back ultimately with this simplified equation. But yeah, that's kind of cheating. So let's take a look at Appendix A. Here we go. This is where we started from. Coming into Appendix A, the first thing they're going to do is expand the triple product. M cross S cross M is known as a triple product, and that appears here and here. And there's a well-known identity for that you can just replace that with m dot m times s minus m dot s times m. M dot m, remember that m is a unit length, and m obviously points in the same direction as m, so this is going to come out as 1. So this reduces to s, bing. And the m dot s, we had just said we were going to call that d. So we got s minus dm. All right, so this is our new value of p, and we can move on from there to this is the rest of the numerator here now. The rest of the numerator was this p crossed with m cross z. So that's what we're going to do next, which is p cross m cross z. And we're going to use, again, we're just going to use the vector triple product. Vector triple product. Triple. Here we go. Vector triple product right there. And here's the identity for it. We're going to use that again right here. So that's what we've done there. P to M is, this is what we just figured out what P is. So we'll put that in and then we distribute. So the M dot S, we had called that D. And then this one will become minus D times M dot M. M dot M is 1. So that's D. So D minus D, 0. P dot M is 0. This term drops away, and we're left only with this term. Okay, so P cross M cross Z equals P dot Z. So then we're going to fill in what P is now, and then dot that with Z. So that means take only the Z component, and that's what that reduces to. So the entire numerator, this entire numerator for the tangent alpha comes down to this piece here. So now we're going to move on to the denominator right here. Where we remember this was called P, so we'll put that right here. So we have this P dot S cross Z. And then P, we had evaluated to this, so now we have this. We can distribute across this dot product, and we'll get S dot M cross Z, which we've written here. But then the second term, it should be minus dm dot m cross z. And then they've explained right here very briefly why that is 0. What we have is minus dm dot m cross z. And if we go back to our little identities, dot cross, this one here, This one right here, dot cross, shows that we can, if we choose, we can reorganize them this way, or we can reorganize them this way. I found this one, I think, was the easiest. Yes. Where were we? Right here. I'm going to take A dot B cross C, and I'm going to change that to A cross B dot C. That's right here, where A is minus dm, B is m, and C is z. So I'm now going to be crossing m cross m, and a vector cross with itself is 0. So that's what they're saying right here. That's 0. So that means that piece goes away, and we are left with only s dot m cross z. We have s dot m cross z, and m cross z is expressed out in Cartesian in individual terms. That's this. And of course, s is the full expressed thing. If we dot the s with this vector, just expand it out, we get this. So the entire denominator just turns into this. And now we are, boom, we have got our tangent of alpha expressed in that simplified form. Go back up in here, that's where they got all of this. So at this point, we're in terms of x, y, and z, but we'd really rather be in terms of the angles, of the elevation and azimuth angles. We're just going to swap those out right here and proceed with that. Now it's going to take us into an appendix. You can skip ahead. We're going to end up here and go through the appendix and see how we got that. Okay, we start with this D. D is right here. D is right here, which was m dot s. If we expand out m dot s and replace with all those trigonometric terms, this is what we have. Right here, we just reorganize. We see that the cosine etas are repeated here and here, so we distribute those out, and that leaves us with the two cosines times the two sines, or rather the two cosines multiplied together plus the two sines, and we'll put that here. That brings us to, that's trigonometric identity. Here we have that right here. The cosine of two angles, and in this case plus the sine of the two angles, gives us the cosine of the difference of those two angles. So we can take this piece and just replace that with the delta. This is the delta of the azimuths. Moon's azimuth minus the sun's azimuth. So that simplifies a little bit, and that's not too bad now. So that's our D. We take D times mz, so that's right there. So D times mz, and then sz goes in right there. All right, again, we can see a little bit more simplification that we can do. And what we'll do is we'll take this term right here and this term, and we're going to combine those. We're going to pull out the sine eta s's, and that'll leave us with, this will become 1, and then this will become minus sine eta m times sine eta m. So this becomes 1 minus sine squared eta m. And then the rest of this we'll leave that as it is. 1 minus sine squared can be replaced as cosine squared. So that gives us this term here, which is our numerator, is this term. All right, that takes us to the denominator. We'll do that right down here. Denominator, filling in the terms, reorganizing again. From right here, we find the sine phi m cosine phi s. So that's sine phi m cosine phi s, leaving the other two terms out. And then on this one, we have cosine phi m sine phi s. That's these two, and that leaves the other two. So we've distributed out the two cosines that were here and here. The cosine etas distributed out. And again, this is the other one of those trig identities that we see right here. If you do sine cosine plus cosine sine, or in this case minus, we're going to need the sine of the difference. So that'll be this replacement right there. Okay, so the denominator's not too scary. So we fill them in. Here's our numerator that we just calculated. Here's our denominator we just calculated. And we can do a little bit more. We've got a cosine squared a to m here, and there's a cosine a to m here. There's a cosine a to m here. So let's pull out a single cosine a to m, and these will cancel, and this will cancel one of those a to m's. So that'll leave us with one cosine a to m, so we've got that there, and then nothing from that term over here. And the sine a to s we'll have divided by a cosine a to s here. So we can replace that one with a tangent a to s. And over here we have a cosine a to s and a cosine a to s, so we can just cancel that one. So when we've done that reduction, we've gotten rid of this part of the denominator, and we've gotten it down to just this. Cosine a to m, tangent a to s, minus sine a to m, cosine of the delta. We'll take an absolute value of that and then divide by the sine of the delta. Okay, so we have our final tangent alpha calculation, but we could do, there's a slight improvement that we can do here, which is, as I described right here, they want positive values of alpha to be when the moon is lit from above, and there's an absolute value here that mixes with things. What they can do is they just took the absolute value and they put it onto the delta. Just redefine the delta to have the absolute value, and then you could drop the absolute values from here. And I have worked that into my little sim as something I call the angle display. Let's show that. I have this formula punched in right here. Got to be a little bit careful because the axes for my system are slightly different from these axes, so don't want to get confused, but you can look at this. I have my numerator right here, continues there, that is this, and then the denominator right there, and then finally I take the arctangent and convert it back into degrees, and I put it in a little text element so that we can see, and I have that right here. Okay, so there it is. The math all worked. We've gone through the entire derivation of this angle all the way from the beginning all the way to the final answer. We plugged it into our simulation and we're displaying the final answer. And I haven't really shown this up until this point, but I want to stress that this simulation that I've created is in fact real-time and dynamic. So I did this so that you could, rotate the moon around, and depending on the height of the moon above the horizon, you're going to get the different angles. And the entire simulation updates in real time. And as the moon azimuth changes, you can see that changing there too. And that changes the angles. You can do the same thing with the sun. Move the sun. Sun's down on the horizon. If the sun was up higher, it would change it in that way. Sun's down lower. Changing the sun azimuth. They correspond again to those same angles, which are July 24th in Los Angeles at 8 p.m. So at 8 p.m., the sun will be setting at an azimuth angle of 294.6, and the moon will be well up 20 degrees above the horizon at 136 azimuth. And at that point, we expect to see this, the light coming in at 42 degrees. Now I can turn off my visualizers. We can see that moon again. Okay, that's that dot. And let's turn off the plane. Turn off the red plane so you can see through it. And you can see there's our moon. Oh, we don't need this one either. Let's turn that plane off. You can see there's the moon, and here's the light coming in from the sun. Turn that light on so you can see the light is coming in straight in there at a 42-degree angle against the horizontal. When we can see that it should be coming in from below. The sun is well below the moon at that point. The sun is just kissing through the horizon right there. And yet, because this line is going up through the view plane at the angle that it is, this is the result that we get. We've done the math and we've done the simulation, and we see this is exactly what it's going to look like on the 24th at 8 p.m. Now, we mentioned this before, but this diagram is not to scale. How can this be accurate if this is not to scale? Well, I have mentioned this before, but the angles are what is important. And we can do that. Let's get rid of this little thingy here. We don't need that thingy. The angles are what's important. So if we just take the sun, which is currently at 100 units away from the observer, and let's just move it out. Move it out to 1,000 units. Pulled it way out there. And the number didn't change. Let's take it to 10,000 units. And the number didn't change. Why is that? How is that possible? Because the view didn't change. Watch this bar. Watch that bar as I go back to 100. Check the angle. Put your finger right there. And as I look how it doesn't, the angle does not change with distance. And that's all that really matters. So that's the observed angle of the moon, which I find to be the interesting part. The paper is going to continue on with the expected slope, which is sort of what the viewer assumes they're going to see. We've already seen what the viewer is actually going to see. That's why I find that piece interesting. It's the actual part that really matters to me. But they're going to go on in the paper and say the expected. So what they do is very simply, they take the original vector, pointing from the moon to the sun, and they project it orthographically, which is to say, means just ignore perspective. So we are going to project it back to a viewer who is looking in the direction of the moon, but is not taking into account the fact that the sun is behind them, right? So this is just a projection straight of that that V vector. Look from the front view, you can see that it's pointing down. From the top view, you see that in this case they were pointing, further forward of them, whatever. The interesting angle then is only what from the front view, when you're looking at it, this dip down angle right there. And so here comes the derivation. This video is getting very long already, so I'm going to breeze through this. So the projection is simply we're dropping out the Z component. We just want these two angles, boom, boom, or these two sides of it, and it's simple projection. So here's the magnitude of that. So square root of sum of squares. So the normalized vector, bang, bang, right there. The vector Vn in figure 9, here's figure 9 again, Vn, this little guy, is V dot n in the direction of n. So take the dot product to get the amount of V that points in the direction of n, and then we want a vector pointing in the direction of n. So then the VP, back to the diagram, the VP, this is the vector we care about now, is V minus Vn. So it's the rest of the vector. We're just taking out this piece. So here we go, we subtract off that piece. Okay, the desired angle is given by the same ratio. This should look very familiar now. The same trick that we did before, where you just take the cross product and the dot product, you divide them, and that's going to give you the tangent of the angle. Substitution trick and reduce it down to here. Do this really fast. We got started from here. We are going to take VP for its components that we just did, and we're going to do the triple product, and then we do the same kind of reductions that we did before and end up with, very simply, that, using the fact that VP is perpendicular to N, so that any dot product of VP and N is 0. So that just drops out. Okay, N is perpendicular to Z, and so the dot products of N and Z, they also drop out. Okay, next we do this is the definition of what V was, and this is the component constituents. So we just take the dot product with Z, so we only want the Z part, boom, done. And here the denominator, this is what's called the scalar triple product, which is like the triple product, only it's dot cross instead of, and we saw that in the vector identities. So we just expand it, and again, we can drop out this term. Okay. And they're expanding y. N cross N, 0 again. Okay. N cross Z expressed out. This is what Z is what N is. They do the cross, boom. And then we dot V, which we got earlier, this V, with that, and you come up with bada bing. So there's our denominator there, and so we're going to take it and combine it with the numerator that we got. So this part goes in the bottom here. This part, we put it up at the top here, and there we go. Got it. So that brings us to this reduction right here. And then again, we're going to go out of Cartesian coordinates into angular coordinates. It's going to get us to here. Let's see that happen really fast. Here's where we started from. We simply do the replacements. We're going to start with the under the radical part right here. Boom, 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 boom. We just replace what mx is and my. We square them, we add them together. And this reduces rapidly down to just this, because this part comes out, and then it leaves a cosine squared plus sine squared, and cosine squared plus sine squared is 1. So we're left with just the cosine squared, and then we square root that, so we're left with just the cosine. And the other part of the numerator right here, we'll just write it like so. Here's the denominator, and we derived that exact expression earlier, so just repeat. And that gets us to here. We're now here, and a quick reduction again is that there's a cosine A to M, cosine A to M. We'll just strike those, and we're left with finally that. Okay, we're going to do the exact same absolute value thing that we did before, and our final answer is right there. So reminding you, beta is the expected angle. This is the angle that the viewer might be anticipating that the light would come from. This is not where the light is coming from. The light is coming from alpha, but the viewer might think that it would come from this angle. And so then they subtract those. That's the amount of illusion. Let's take a slightly different approach now before we wrap up. And this time I'm going to do just what I call the engineering approach, whereas the paper we went through was the mathematics approach. Here I'm just going to use a little linear algebra to just get my answer rapidly. I'm going to start from the same place, which is I have my v vector pointing from the moon to the sun. What I'm going to do differently is I'm going to create an observer matrix, which means I just take my observer's orientation, I arrange it to point straight at the moon, and then I make a matrix out of that. And all I got to do now is transform the vector v, this is a vector v, that's just been transformed so that we're in new orientation, that the observer's forward direction is the forward direction. And I'll call that new vector v prime. So this is v prime, and I mean right away you see that it points in a new direction. But this makes the math really trivial. All the sines and cosines are in here, they're right in here in this matrix, and then I just do my arctangent of that division. Taking that engineering approach to our simulation, what do we get there? Well, that's what we had in the first place. That's where we started from. That's the first approach I showed you before, which is this line is the line between the sun and the moon. And in this view, we are projecting that line into the viewer's space, into the viewer's point of view. All that is to take this vector, these 2 points, every point along the line, and project them back into this view. That's what we've been doing. So we get the exact same answer that we've been having all along. Why have we been spending so much time with this paper, going through all of this vector math and all of this trigonometry? Well, to be fair to the authors of this paper, they had the answer right here. That was the first time when the angle was known. The angle of what ultimately became alpha was right there. We knew P, we knew H. We could plug it in and do arc cosine right there at this point and been done with it. If all we wanted was the numerical answer, that's all we needed to do. But what they wanted to do was they wanted to get the answer reduced to a simplified form and then get it into terms of the input angles. And that's what all this math was all about. The math was about generating this equation here in terms of the input angles and getting it as simple as they could make it. If you just want the answer, you had it here. Or you could just use the vector math method, the linear algebra method, where you do a couple of matrices, do a multiply, and you get the answer. Looks like this. This is my simulation of it. Here's the number gotten from the Myers paper. And here's Stellarium doing the exact same thing. These are all the numbers chosen for July 24th at 8 p.m. in Los Angeles. And they all match up.